For some tasks, a sigmoid learning curve is used to model proficiency. Suppose the percent proficiency is given by the model P of t equals 100 divided by 90 e to the negative 0.1 t, where t is in days of practice. Find the inflection point, the point where additional practice starts producing diminishing returns. Give your answer accurate to at least 2 decimal places. All right, before we start jumping into this is probably a function that some of you are unfamiliar with. So it's probably a good idea to get familiar with it before we start trying to jump into the problem. So let's take a look at a graph of this function. Okay, here's its graph. And what we're looking for is an inflection point. So the inflection point is where concavity changes. Based off of this graph, it looks approximately right there. Because on this interval, it looks like I'm concave up. And then on this interval here, I'm concave down. So that looks like an inflection point. It's somewhere between 40 and 50, maybe approximately 45. It's hard to really tell. But this gives us an idea of the point we're looking for. So once we get the solution, we can be a little bit more confident that we've done the process correctly. Okay, let's get started. In order to calculate an inflection point, we need to find where zeros are for our second derivative. So inflection points, these are zeros of our second derivative, or potentially where the second derivative is undefined as well, but most of the time it's just where there's 0. So I need to start by figuring out my first derivative. What I will do is rewrite the function so that I'm not using the quotient rule initially. So 100, 1 plus 90e to the negative 0.1 t to the negative 1 power. All right, now the first derivative, we can use the chain rule. So I would bring negative 1 down, multiply it against the 100. So negative 100, 1 plus 90 e to the negative 0.1 t, subtract 1 from that exponent, multiply by the derivative of the inside part. So the derivative of the inside part of this function right here is going to be 90 e to the negative 0.1 t, but that inside part also requires a chain rule, so then I need to multiply by the derivative of the inside of this function, which is negative 0.1. All right, now let me work my way back outward and start simplifying, because I'm going to do a second derivative, so I want this thing as simple as possible. All right, negative 0.1 times 90, you're effectively dividing by 10, so that's going to be negative 9. And then negative 9 times negative 100 is going to be positive 900. So that means I have, let's see, 900 e to the negative 0.1 t in the numerator, and that's going to go over 1 plus 90 e to the negative 0.1 t squared in the denominator. And I'm just rewriting that square as a positive exponent, bringing it into the denominator. Now, all things considered, that isn't too bad for a first derivative. But I now need to start working on a second derivative. The second derivative, I'm going to have to use the quotient rule. So I'll go ahead and get started drawing my box here. The numerator is 900 e to the negative 0.1 t. The denominator is 1 plus 90 e to the negative 0.1 t to the second power. The derivative of 900 e to the negative 0.1 t is going to be 900 e to the negative 0.1 t times the derivative of the inside part, which is negative 0.1. And I'll go ahead and simplify here. Negative 0.1 times 900, that's going to be negative 90. Okay, then the next part here, I'm going to have to use a chain rule. All right, I bring my 2 down, and I have 1 plus 90 e to the negative 0.1 t. Subtract 1 from my exponent, so that's down to the first power. That's great. Times the derivative of the inside portion, which is this. So that's going to be 90 e to the negative 0.1 t. But then that has its own inside portion. So I then have to multiply by the derivative of that exponent, which is negative 0.1. That's that derivative. If you'll notice, there's a lot of coefficients here, so I could take negative 0.1 times 90, which would give me negative 9. And then negative 9 times 2 is going to give me negative 18. Okay, now that that's done, let's form our derivative. So we're going to have the second derivative. We multiply these two boxes together first. So let's see. I have negative 90 e to the negative 0.1 t times 1 plus 90 e to the negative 0.1 t quantity squared. And then it's minus, for the quotient rule, coefficients, I'm multiplying negative 18 times 900. I've already done that off to the side, and that's negative 16,200. Okay. And then I have an e to the 0.1 t, and then another e to the negative 0.1 t. And to simplify that, e to the negative 0.1 t times e to the negative 0.1 t, what's nice there is if you have exponential functions with the same base, you can combine them by adding your exponents together. Because these exponents match, you're effectively just multiplying by 2. So I can really make this e to the negative 0.2t and simplify it. All right, so when I multiply e to the negative 0.1t times another factor of that, I get e to the negative 0.2t. And then it looks like I have another factor of 1 plus 90 e to the negative 0.1 t. All of this is going to go over the original denominator, which was 1 plus 90 e to the negative 0.1 t quantity squared, and then we're going to square it again. So that will go to the fourth power now, which looks intimidating, but it's going to get a little bit better. If you'll notice, there is a common factor of 1 plus 90 e to the negative 0.1 t in each term. So that means one of these, leaving me to the third power, cancels out one of these, which makes that to the first, and one of these, which makes that to the 0th power, which is just the same thing as 1. So that whole term cancels away. So things are looking a little bit better. I've got the ability now to take this term and multiply it into these parentheses, because that's now to the first power. So that's going to be negative 90 e to the negative 0.1 t minus 90 times 90 is going to be 8100 e to the negative 0.2 t minus times a negative, of course, makes a positive, so then I have plus 16,200 e to the negative 0.2 t. And think you at least see that even though it was started out pretty bad, it's getting less bad, because now I have two terms that are common factors right here. They have the same multiplying factor. I can combine them into a single term, and negative 8100 plus 16,200 is positive 8100. So now I have negative 90 e to the negative 0.1t plus 8100 e to the negative 0.2t all over that denominator cubed. Lastly, I can do some common factors from the numerator, and the most factored form is considered the simplest form, especially when you go on to solve later on. There's clearly a common factor of 90 among both of those terms. And there's also a common factor of e to the negative 0.1t. So that leaves me 1 in the first term minus 90 e to the negative 0.1t. And that e to the negative 0.2t reduced to e to the negative 0.2t for the same reason that I showed you a little bit ago as to how those things multiply to double, they divide by half. So not going to go through that again. And there we go. That is our second derivative. Now, finding the second derivative was only half the battle. What I need to do next is I need to determine where this thing has inflection points. And inflection points occur where the second derivative is equal to 0. So I need to take this function, negative 90 e to the negative 0.1t times 1 minus 90 e to the negative 0.1t all over 1 plus 90 e to the negative 0.1t cubed, set that equal to 0. Here's the great thing. The great thing is, if I multiply both sides of this equation by the denominator, I don't really have a lot of room to write over here on the left-hand side, but I'll squeeze it in. 1 plus 90 e to the negative 0.1t cubed, so I'm multiplying this side by that, and this side by that. The great thing that happens is something that students don't fully understand the scope of in college algebra when we tell you this thing. A rational function, or a fraction, that is, it's only going to be 0 where the numerator is 0. Because this denominator cancels out, 0 times anything is still just 0. So the next stage in this process is just to take the numerator, negative 90 e to the negative 0.1t, times 1 minus 90 e to the negative 0.1t equals 0. That's a much better thing to work with. We've gotten rid of the denominator altogether. Now, these are two factors. So here's one factor, and here's another factor. They are multiplied together, and their product is 0. By the zero factor property, that tells me one of two things is true. That either the first term is equal to 0, or the second term is equal to 0. Same thing that we used when we were solving quadratics. Now, if I try and solve the first one, I can divide both sides by negative 90. Get rid of that. So e to the negative 0.1t is equal to 0. E to a negative exponent is the same thing as 1 over e to the positive exponent. But the thing is, now if I multiply both sides by e to the 0.1t, look what happens. Cancels out here. That product is still 0. I get 1 equals 0, which is a contradiction. What that tells me is this particular equation just simply doesn't lead to any solutions. And it should also make logical sense, because if you're looking at just this portion, you have an exponential function that's set equal to 0. Exponential functions never equal 0. There's a horizontal asymptote there. That's another important thing that we told you in college algebra that kind of gets forgotten. But the principle is the same. Let's move on to the other. So I have 1 equal 1 minus 90 e to the negative 0.1 t equals 0. So let's make it 1 equals positive 90 e to the negative 0.1 t. Now I'm going to make that 1 equals 90 over e to the positive 0.1 t, or e to the 0.1 t equals 90, which is good, but we can't solve it for t unless we switch into logarithmic form. So I'm going to take a natural log. So the natural log is base e. I'm doing that purposefully here because when I first take this exponent and make it a constant multiplier of my logarithm, I have 0.1t times the natural log of e. The natural log of e is just 1, so that's why I chose the natural log here. The next part to get t by itself is to divide both sides by 0.1. So now I get t is equal to the natural log of 90 divided by 0.1, which I don't particularly know my natural log tables in my head, so I'll get the calculator out, and natural log 90 divided by 0.1 gives me 44.998. So approximately 44.998. And we can be pretty confident of that solution because looking at the graph, we saw that it was supposed to be just about at 45, and that's pretty close to 45. So I think we've gotten the correct answer here.